There are various types of energy that we can talk about in physics, but today for this unit P2 for GCSE Science, we're going to talk about two kinds, and those are kinetic energy and gravitational potential energy. Now, kinetic energy is another word for movement energy. So anything that is moving has kinetic energy, and gravitational potential energy is the energy that something has because of its position in a gravitational field. That's just a slightly long way of saying the energy something has because of its position above the ground. So something high up will have more potential or gravitational potential energy than something lower down nearer to the ground. Now, in terms of these two, you need to be able to use the formulas to calculate them, and for the first one here we've got the formula down here, which is just off the screen there. Right, so we have EK is half times m times v squared. So EK stands for kinetic energy, m is mass, and v is velocity. You'll be given all of this in the exam, but you won't be given the unit. So you've got to remember the unit for kinetic energy is joules, mass is always in kg, and velocity is in meters per second. Okay, so that's the formula there for this one, and the formula for gravitational potential energy is EP is m times g times h. The only little complication there is we've got g, and if you remember from the previous video, that means gravitational field strength. Now for planet Earth, that is always 10 newtons per kilogram. In actual fact, it's nearer to 9.8, but they usually ask you to use 10 in the exam, and if they want you to use something different, they will tell you. So m again is mass in kg, gravitational field strength we've said, and height is in meters. So these are the two key formulas that you should be able to use for kinetic energy and gravitational potential energy. Now, moving on from that, and then let's just do a couple of examples for kinetic energy. I've just got the formula up here so that we can refer to it. If we've got a car that is, say, 500 kg moving at 20 meters per second, very simply we plug it into the formula. So it's half times 500 times 20 squared. Don't forget to square the velocity at the end. Students often forget to do that and get a slightly wrong answer, and if you multiply all that out, you get 100,000 joules, or 100 kilojoules. Two more examples to share with you. The next one is what I've tried to draw here is what a meteorite might look like. So imagine you've got a meteorite, it's quite a big one, 1,200 kilograms, traveling at 5,000 meters per second through space, hits the Earth's atmosphere with a kinetic energy of, and we can write out the formula. So it's half times 1,200 times 5,000 squared, and that comes out as, and I'm probably going to need a bit more space to put that answer, 15 million joules. Okay, so you can actually put 15 megajoules. Okay, so that's quite a lot of kinetic energy by this asteroid speeding through the Earth's atmosphere. And the last one over here, we've got the space shuttle, and I'll tell you why I've chosen this as an example in a minute. But the space shuttle, again, we're going to do the same thing, so I'll just quickly skip to the answer. 3,750 billion joules. So that's a lot of kinetic energy that the space shuttle has. Now, three examples here, quite small numbers and larger numbers towards the bottom. They don't usually give examples with these big numbers, but the reason why I've used a space shuttle here is because they do mention in the spec about energy transfers, and they talk about how kinetic energy can be transferred into heat energy, for example in meteorites or in the space shuttle. So imagine we've got the space shuttle coming in to the Earth's atmosphere. We've got 3,750 billion joules of kinetic energy, lots of kinetic energy, and as that hits the atmosphere, you get friction against the Earth's atmosphere, against the air, and because we've got all that kinetic energy, all that movement energy, high amounts of friction, you get energy transferred from movement into heat energy. And as you can see, there's a lot of energy being created or can be created because there's a lot of kinetic energy in the space shuttle. Okay, so that's just a quick overview of how you calculate kinetic energy. There's a few examples there, and the next one then is gravitational potential energy, and I've just got a couple of examples which I'll zip through for you. First one is a table with a book on it. Imagine you are lifting the book from the floor to the table surface, and we have the formula here. So it's mass times gravitational field strength times height, and I'm going to suggest that we use 10 for this example, as they probably will in the exam. We've got mass of 1.5 times 10 times 0.9, and therefore the gravitational potential energy for this object here, the book on the table, is 13.5 joules. So not very much at all considering the kind of numbers we've been working with just now. And one last example, we've got a hydroelectric power station here. So we've got water going through and turning some turbines, but imagine you wanted to calculate the amount of gravitational potential energy in 100 kg of water that's at the top of the reservoir here. So we would have it's a simple case of just plugging the numbers into the formula. So the mass is 100 kg times 10 times 200 meters, which is the height. Work all that out and you get an answer of 200,000 joules, and you can simplify that to 200 kilojoules. Okay, so that's a quick overview of how to use those two formulas. There's just one last thing I wanted to go through quickly, and that is comparing kinetic energy and gravitational potential energy of an object. I've got a tennis ball just before it's being dropped to the ground, and it has a gravitational potential energy of 100 joules and a kinetic energy of 0 joules because it's not started falling yet. But after it's been dropped, the amount of gravitational potential energy reduces. So imagine we've got 70. If we've got 70 joules of that, how much kinetic energy are we going to have? Well, that balances out to 30 because the two add up to make the original 100. And right near the bottom, we've got a low amount of potential energy, but a higher amount of kinetic energy because it's increased in speed and lost some of its height. This all assumes that there is no other energy transferred to anything else. For example, heat. There is a tiny, in actual fact, there is a tiny amount transferred to heat, but we, for the purpose of this, we're ignoring that little bit of energy. But that's just a little extra example because they suggested this as a practical that you might want to do in school, so I thought I'd bung that in at the end.